kind of late, so I'm gonna try to keep it short and simple. It's scientific, I mean, it's a master research, so I'm gonna try to do my best to keep it real simple. So, why methane? Well, from all the sources that release methane to the atmosphere, wetlands represent 30%. It's not a small number. And to partition this 30%, more than half of the wetland methane emissions are coming from the tropical and subtropical wetlands, like the ones we have here. So methane, or CH4, is a form of carbon, and it's a greenhouse gas that loves CO2. It can trap 28 times more heat than CO2 over a period of 100 years. So, this carbon, okay, this is a simple graph of the wetland soil system. This is the anoxic layer. This really thin one here is the oxic layer, and this is the surface water. So carbon gets into the system through the plants, and some of that carbon is released back by plant respiration. Some of that carbon can accumulate, potentially leading to what we know as carbon sequestration, and some of that carbon is decomposed by the microfauna that lives in the soil. When that carbon is decomposed under waterlogged conditions, so no oxygen, you can have methane as a product. And then that methane can travel up through the water column and be intercepted and reused, or be finally released into the atmosphere. So my talk today is going to focus on the net methane emissions, which is the final release. As you can probably see from this somehow complex graph, there are a lot of factors that affect methane emissions. But the literature coincides in that hydroperiod is the most relevant one. Hydroperiod is nothing else but like the signature of the water. So by knowing the hydroperiod, you can know the period and frequency of inundation of a wetland. And changes in those parameters can alter the source of the role of the wetland as a source or as a sink of these greenhouse gases. So, generally speaking, the objectives of my research were to assess the variability of methane emissions from 2 cypress swamps. So, this is a general picture of my study areas. As I said, it's 2 cypress swamps that I have. One is located in this area, and it's in FGCU campus, and the other one is located in this area, which is where we are right here, right now, which is Corkscrew. This area, at a regional level, has changed dramatically through the years. You can see here, there's some channels, there's some industry, there's some quarries over here, there's urban development. Before people started coming in to live in this area, this was a combination of upland and wetlands. Now you can see it's a mosaic of agricultural patches, industrial, urban, etc. So it's been altered through the years. However, there we go. Another important thing to mention here is that both of these basins, this is the Cedar River Basin and this is the Corkscrew Basin, both of these basins are principally fed by precipitation. So in this area you can see that the water flow gets intercepted by several barriers before it gets here to FGCU campus. But here there's no much disturbance upstream Corkscrew. So for those reasons, I have, for the purpose of my research, I have named the swamps at FGCU as the disturbed swamps and the Corkscrew swamps as the reference swamps. This is, there's not really reference anymore, but this is as good as it can get. This is just a progression of the local changes through the years on my study sites. Focus here on the area of FGCU campus, so it was wetlands, it was cypress domes, marshes, slough, And through the years, you can see that construction has started occurring. There's some quarries over there. However, here in Corkscrew, it has stayed the same through the years. And hopefully it will stay the same. So in each one of my swamps, I have 3 sites. As you can see, 2 here within the campus loop, which are cypress zone, and 1 outside in the conservation area. In Corkscrew, I have 3 sites. 2 are close to the boardwalk. 1 is actually by the boardwalk, Class Boardwalk, I think is the name, and the other one is Fish Farm Road, and there's 1 outside of the area. It's a Paulfront site. So basically, what I did to sample the methane is I used a static chamber, which is a combination of a bottomless frame that was permanently installed in the field in each one of the sites, and deployable tops that you can see over there. I also had loggers to measure the water level and soil temperature in each of the sites. And I had 3 chambers per site. They were separated approximately 1 meter. And this was to be able to incorporate the variability of the methane, the spatial variability. So when I took the samples, I just sealed the frame, the bottomless frame. I sealed it with the deployable tops. And I took the samples in the morning and in the afternoon. In 2014 was the whole year from January to December. And I took 6 samples per chamber. Then I used those samples, I analyzed them in the lab. This machine gave me the methane concentrations, and with a series of procedures, I calculated the methane emission rate. So I'm gonna talk a little bit about the results. As I said before, the areas where my sites are principally fed by precipitation. So you can see here, this is the precipitation pattern, and it's a clear, rainy and dry season. The majority of the rainfall is occurring during June and September. This is going to translate into the hydroperiods. These are the hydroperiods for the sites here in Corkscrew, for the reference class. Each color is one of the sites. And something important here is that the 0 is the surface level. So all this gray area is water below ground. The hydroperiod lagged a little bit behind the precipitation. There's always a delay until the sites start filling up with water. An interesting thing here is that the sites here in Corkscrew are hydrologically connected, and they have a good amount of water. The Bald Cypress site, which is the one at the Class Boardwalk, is the one that had the highest water levels and the longest inundation period. It stayed for like kind of 80% of the whole study period. It stayed inundated. These are just some pictures that were taken in October. They were taken the same day. This is at 75 centimeters, as you can see here. I'm actually standing at the boardwalk there, and the water is already at my knee height. So there's a lot of water. You can see here, this is a completely different story. These are the disturbed swamps, the ones at FGCU. So much drier, it's the same scale, it's at 1 meter, it's much drier, and it's really, really short inundation periods. So, as I said, when I was showing the graph, the wetland soils, carbon is a substrate for the microorganisms to produce methane. So I did an exploratory research to know how much carbon was in those soils. So I took a soil core in each of my sites. The most important thing here, it's just kind of a complicated graph, but the most important thing here is that all the 3 sites in Corkscrew have a high percentage of organic carbon. While the sites are, this is the pond cypress loop, which is kind of outside of the loop of campus. It still has a good amount of organic carbon. And these are the ones, the cypress domes, that are completely isolated within the campus loop. And you can see that it's very poor. So these sites probably have more substrate availability for the microorganisms to produce the methane. That's the most, like the big picture related with carbon in my soils. Here we can see the monthly distribution of the methane fluxes. Each one of the months is represented by 6 values. So here you have the mean, the median, and these bars are the standard error, water level, and the methane fluxes. Something that jumps to our eye is that methane is highly variable. Sometimes I had like a value of, it was probably around 20 milligrams of methane per meter square per day, and a meter away in the other chamber I could have a value of like 180. It's common, you find in the literature that methane is very variable. Another interesting thing is that almost in all the cases we had methane when there was water above ground. These are the only 2 exceptions that we had methane when there wasn't, but they were very low, and we are assuming that this happened because the soil was still saturated, even though there was some water above the ground. The water level was high to the surface. And some of the sites here in Corkscrew acted as temporary sinks. So we were having negative values. They were actually uptaking methane. This is the same graph. Note that the scale of the axes are exactly the same, but this is FGCU. These are the disturbed sites. Of course, much less water, much less methane. These are the positive cases. There were a lot of cases that the methane was 0. And an interesting thing here is that one of the cypress domes that was within the campus loop was a net sink of methane. We were still talking about values that are really low, lower than 20, but it's still considered a sink of methane. So, kind of like to summarize and have a clearer picture of what's going on with the methane fluxes between the sites that I have, this graph is telling us that there are significant differences, that the methane fluxes were statistically higher in the reference swamps, so Corkscrew, than in the disturbed swamps. Also, another interesting thing is that within the disturbed swamps, there is difference between the pond cypress loop, the one that is outside of the campus loop in the conservation area, and one of the cypress domes, and it's basically because this one is acting as a net sink. And well, to end on a kind of a positive note, because we all know that methane is not that good, but I've added a little bit of information about carbon sequestration that a lab mate from the research lab I work in. He did a thesis actually here also, and we shared 2 sites, so it's exactly the same sites. He did it 2 years, so he did his thesis 2012 and 2013, and mine was 2014. So I used some of his data to kind of compare and have a global picture or a clear picture about methane and carbon. So this is the methane range in forested swamps in US and some other countries like Venezuela, Costa Rica, but only forested swamps. And we can see that Corkscrew is in the lower part. So Corkscrew is emitting 10 grams of methane per meter square per year. And from several literature also, we know that the range of mostly the same sites, we know that the range of carbon sequestration goes from 18 to 132. And Corkscrew, from my lab made research, I got that Corkscrew it's actually sequestering 87 grams per meter square per year. So I just wanted to add that because whenever you analyze methane, it's always good to factor in the uptakes also. You shouldn't just think on like one part of the ecosystem because it's a whole. It's giving and it's taking. So finally, some of the biggest conclusions is that we did find a relationship between the methane fluxes and the water levels, the hydroperiods, so higher water levels, longest inundation periods resulting in higher methane fluxes. Well, that's the same, that actually goes by the same idea. The soil organic carbon could be potentially explaining, sorry, just yeah, so here in Corkscrew we didn't have significant differences between the sites, but there's probably another factors that are combining, and that could be the explanation. The hydroperiods were similar and the organic carbon was similar. So probably there's other things going on that we didn't measure, and that's why we don't have significant differences there. And finally is that the reference point cypress slough, so here Corkscrew, acted as an occasional sink of methane, and the cypress dome at campus acted as a net sink of methane. And I'd like to finish acknowledging all the people that was in my committee. Actually, Sean was great help here, and some of my lab mates have helped me through the work, through my sampling. Thank you very much.
All right. Well, we do have time for a question or two.
I have a quick question. Is anyone looking at this as a soil biota between the disturbed sites and undisturbed sites?
Honestly, not that I know. No, the research on campus was completely new. They haven't worked in those sites. My Jorge Villa, which is the lab mate that I use the carbon sequestration numbers, he did a appreciation, but not. I mean, he factored in biomass, but that's
Not
it.
specific biota.
Yeah, not specifically biomass. Oh, sorry.
I was just going to ask, how do you determine the depth of the container for when you are doing sampling? And if you were to change that and incorporate more, would you expect that there would be a difference in emissions?
Yeah, I mean, okay, so it is a method. It's Cha is one of the authors, and it's a method that we follow. So the bottomless frame, the base that you install there permanently, that is very 10 centimeters. That's always like that. If you find too many roots in the place that you are putting your chamber, or you're burying your chamber, what you usually do is you move it. Try to put it in a place with less roots. So what I would say, what I believe is is that if you put it like deeper, you could end up having more trouble with all, the roots, and that could affect your methane fluxes.
So you said it's bottomless?
Yes.
Oh,
It's
okay.
it's bottomless, and like you put it in, you leave 10 centimeters out, and then when you are sampling, like in the exact moment sampling, you take the deployable top and you put it on top and just seal it.
Oh.